now we're going to talk about position velocity acceleration, specifically a constant velocity and then a changing velocity, which would create a constant acceleration. We're going to talk about that, how it goes from graphically to the formulas, and then we'll be able to use the formulas as we go to solve various things. We know that the position time graph has a slope with a velocity. Now what this is saying, if you recall, we had that y equals mx plus b equation where the b-intercept goes away. On my x-axis is time, and my k value, or my slope, is going to be v, and on my y-axis I have x. Now in order to find this v, what we're looking at is the x over t. But when we find this slope, we actually know that it's x minus x naught and t minus t naught, because it's the change in y over the change in x. Sorry. And so if I rewrite this, I have v average is equal to delta x over delta t, and x minus x naught over t minus t naught. T naught is almost always 0, and so when I rearrange this, I can get vt plus x naught is equal to x. And we flipped that, and we had x equals x naught plus vt, and that was the first kinematic equation that related velocity, position, and time for us. Now, this velocity time graph, we understand that the slope of the velocity time graph is an acceleration. So we can do the same thing. You had v minus v naught over t minus t naught, and that's equal to the acceleration. Again, t naught is typically 0, and so I can rearrange this equation. This would be a second kinematic equation that you can use to find accelerations given velocities and time. So make sure you have these relationships in your notebook. You have an initial velocity in the x dimension that is 3 meters per second, and an acceleration in the x dimension at 2 meters per second. What would the final velocity be as a function of time? So given time 0, time 1 second, time 2 second, times 3 second, etc. Now instead of graphing this all out, we can use the equation. Final velocity is equal to initial velocity plus the acceleration times a certain amount of time. So initial velocity of 3 plus 2 times 0. This term goes away, and so I know at time 0 I'm moving 3 meters per second. And this is for time 0, time 1, and time 2. Now we notice that this is a constant acceleration. If you have a constant acceleration, I can arrive at an average velocity much easier. Because my velocity is changing at a constant rate, at any given interval I can have the average velocity, because the average velocity is going to be the same as the instantaneous velocity. We'll take the average velocity here. V average is equal to 3 plus 5 plus 7 divided by 3. 15 over 3 equals 5 meters per second would be the average velocity for this equation. Because of the principles of averages, and we're working at a constant acceleration, the average velocity is equal to the initial velocity plus the final velocity divided by 2, because I'm taking 2 points on that graph divided by 2. Because of that, and because of what we showed earlier where we graphically proved that the acceleration was the slope of a velocity time graph, I can take these two and put them together. When I simplify this, what I did here was I basically combine these terms. So the 2's are going to cancel out, but the 2 divided by 2 here is 1 over 1. I still actually have 1 over 2 here, so this term gets a half. So axt, and then the v not x goes in here. So it just kind of simplified. This provides an average velocity for an initial velocity plus 1/2 of the constant acceleration times the time that it's acting on. This is another kinematic equation that you can use. And it came from combining the idea of an average and our graphically produced velocity time graph. We can get a position acceleration relationship by combining these two equations. So what I did was I took this section here and I stuck it into here, right, which was up here. So I'm combining these two equations because I want position and acceleration to be in the same formula. And so when I go ahead and simplify this, I get position is equal to the initial position plus the initial velocity for a certain amount of time plus 1/2 of the acceleration of a certain amount of time squared. This provides us with a very important relationship of position to acceleration. You're going to want to write that one down as well. Alright, understanding that velocity and time, acceleration and time, velocity, acceleration, and position and acceleration are all connected mathematically. Let's look at the velocity time graph again and ask ourselves, so where is position or displacement on a velocity time graph? We already know that the slope is acceleration. Under the curve, the area under the curve would be the displacement for any given time increment. So what we do is we take the shape under the curve and we break them up into smaller shapes, and then we can find the area of each of those shapes and then we add them together, and that would be your displacement for that time increment. Calculus is really nice because it can handle curves that are not constant acceleration, and you can use some calculus to find an infinitely small amount of intervals under the curve. So in this algebra class we're looking at velocity, time, and how do we look at this algebraically. So let's take the triangle. The area for a triangle, 1/2 base height. It's pretty obvious here that the base of the triangle is going to be the final minus the initial time. But what about the h? We could say that it's the velocity final minus the velocity initial, but that would add a variable, and I want to keep this in terms of t. So let's use the slope and what we know about our relationships between velocity and time. So we can say that the acceleration is the final velocity minus the initial velocity divided by the final time minus the initial time. Now I can set this in terms of Vf so that I can substitute in for my h. So I'm going to divide this or multiply t's over. Now originally I kind of wanted to set the Vf minus Vi in place because that would have been my height of my triangle, but I don't want it in terms of Vf and Vi. And so I noticed I have Vf and Vi here, so I'm going to take this and I'm going to substitute it into there. Now if I simplify this, 1/2 at squared this looks just like a term that we've seen somewhere else. This is the same term that you can find in the displacement equation. And you say, well, what displacement equation? Now I have a displacement equation that will use the velocity time increments and the slope and the time increments to help us understand the area underneath the curve without having to draw a graph and measure all these lengths and add up my areas. this would be worth adding to your equation chart if you haven't already. Now it's useful to have an equation without time in it. Let's take Vx equals V naught x plus Ax t and solve for time. Using our relationship with position and acceleration, we can substitute all of the time variables for this right here. So I'm going to take this Vx minus V naught x over Ax and sticker in these positions, being careful to square that whole thing once it goes in. After a lot of algebraic canceling out and adding together, what we end up with is, and we now have a relationship between velocity, acceleration, and displacement without time. So in summary, after all that, looking at constant velocity and constant acceleration and understanding how to pull equations out of the graphs so it can represent a real-world equation, we can start using the equations all by themselves as kind of a toolbox to solve for what we call kinematic problems, or linear motion problems where the velocities are constant or the velocities are changing and the acceleration is constant. So these are going to be your kinematic equations. You're going to want to memorize them for the test because they won't be given to you. You need to be familiar enough with them to have an epiphany about which equation to use given a certain amount of information that's been given to you. We'll go through a lot of this in practice time in class, but essentially you have, the understanding of what the average velocity is, change in position over change in time. We manipulated that so that I could relate position to a change in, position to a velocity over time. The fundamental average acceleration, which was a change in velocity over the change in time, came from that graph, and then we manipulated it in terms of velocity with respect to how acceleration over a given time would change that. And then we started combining equations and we came up with the change in position or displacement. There's two different ways to write this. So x final position minus initial position is equal to that, or position equals initial position plus a velocity over a certain amount of time plus an acceleration over a certain amount of time squared. And then in terms of velocity without time, sometimes time is not given to you. I can connect displacement with velocity using my acceleration. So these are your kinematic equations. There's 4 of them that you need to understand. Make sure you have these in your notes. Make sure you know how to use them. Pay attention to the units and try to apply these in the practice coming up.